What if you fell into a black hole? We imagine a violent pull, a sudden crush, a fall that ends instantly. But that is not what happens. At the moment you cross the boundary, reality divides. To the outside universe, your final instant stretches toward infinity. You appear frozen at the horizon, unmoving and silent. But from your own point of view, the fall continues smoothly, without any hint of resistance. It feels as if the universe simply lets you pass through. Both experiences are true at the same time. But this split reality raises a deeper question. What kind of force can bend space-time so severely that two timelines emerge from a single fall? To answer it, we must rethink space itself, not as emptiness, but as a river that flows. To grasp the magnitude of this paradox, we must first understand the sheer difficulty of creating such a tear in reality. It demands a concentration of energy and matter so colossal that it defies imagination. Even in our most advanced machines, like the Large Hadron Collider at CERN, if physicists ever managed to forge a microscopic singularity, it would exist for a mere fraction of a second, only 10 to the power of minus 23 seconds. A lifespan so fleeting that instantaneous feels like an eternity. But out in the dark, the true giants are waiting. They are incredibly distant. The nearest known black hole, Gaia BH1, lies over 1,500 light-years away. To put that in perspective, if you could fly a commercial airliner toward it, the journey would take 1.5 billion years. We are not at risk of stumbling into one by accident. So why do we obsess over objects so far, so rare, and so inaccessible? Because they represent a fundamental crack in our understanding of the universe. By definition, a black hole is a bottomless pit in the fabric of the cosmos, a region where gravity is so intense that nothing, not matter, not radiation, not even light, can escape. It is a one-way ticket to the unknown. Everything that enters is lost to our observable universe forever, and this terrifying permanence forces us to confront the nature of the universe itself. If a black hole never gives anything back, does it eventually drain the cosmos dry? To answer this, we must strip away the science fiction. A black hole is not the caricature villain seen in movies nor a magical vacuum cleaner that indiscriminately sucks up starships. It is a distinct physical reality with properties that challenge the laws of thermodynamics and relativity. We are about to embark on a journey to understand how they are born from the catastrophic collapse of massive stars, how they grow, and how they might eventually die. But first, we must understand the mechanism of the trap itself. How does a hole in empty space actually work? The answer lies in the most powerful metaphor in astrophysics, the river. Imagine the fabric of the universe not as a static stage where stars and planets sit, but as a dynamic, flowing substance. In the early 20th century, physicists visualized gravity as a curvature, a bowling ball sitting on a rubber sheet. But to truly understand the trap of a black hole, we must upgrade that image to something far more violent, a waterfall. According to the river model of general relativity, gravity behaves exactly like a rushing current. Space itself is falling into the black hole, dragging everything embedded within it, matter, energy, and light, towards the center. Far away from the hole, this river moves slowly, a gentle drift that a spaceship could easily power against. But as one moves closer to the abyss, the gradient steepens. The current of space begins to accelerate. This is where the trap closes. The laws of physics dictate a cosmic speed limit, the speed of light. Nothing in the universe can travel faster than this absolute constant. Imagine a photon of light as a salmon, the fastest swimmer in nature, swimming upstream against the current. As long as the river flows slower than the salmon's maximum speed, the fish can make progress. It can escape. But the black hole commands a river that knows no such limits. At a specific distance from the center, known as the event horizon, the speed of the falling space reaches exactly the speed of light. This is the edge of the waterfall. It is the precise point where the river flows downward at 299,792 kilometers per second. A photon of light emitted directly away from the black hole at this boundary is like a swimmer sprinting at full speed on a treadmill, moving equally fast in the opposite direction. It swims furiously, but it remains frozen in place, forever hovering on the brink, unable to advance an inch into the safe waters of the outer universe. Cross that line by even a millimeter, and the mathematics of survival collapse. Inside the horizon, space is cascading inward faster than light. A signal sent back toward home is still traveling at the speed of light locally, but the space it travels through is being dragged down faster than the signal can climb. It is not that the light is held back by a force. It is simply that the road beneath it is collapsing faster than the car can drive. There is no path that leads away. Every direction, every future flows down. However, the violence of this river is not uniform. The terror of the fall depends entirely on the scale of the monster waiting below. We often assume that the larger the black hole, the more violent the death. But nature has a counterintuitive cruelty. The size of the black hole determines whether you survive the fall to witness the interior or are torn apart before you even reach the edge. This is where the physics becomes counterintuitive. Logic suggests that the more massive the monster, the more violent the death. If a black hole contains the mass of 1 billion suns, surely its gravity should crush an intruder instantly. But the mathematics of the abyss reveal a paradox. The most dangerous black holes are actually the smallest. To understand the danger, we need to examine the mechanism that actually threatens a falling traveler. It is not gravity itself, but the difference in gravitational pull across their body, the tidal force. As an astronaut descends feet first toward the region of stronger curvature, their feet lie slightly deeper in the gravitational well than their head. Even in the simplest Newtonian approximation, the gravitational gradient increases noticeably with decreasing distance, meaning the feet experience a stronger pull than the head. In the vicinity of a stellar mass black hole, a remnant merely 10 times the mass of the Sun, the event horizon is incredibly small, perhaps only 30 kilometers wide. Because the source of gravity is so concentrated, the gradient is steep. The difference in pull between feet and head becomes catastrophic hundreds of kilometers before the astronaut even reaches the horizon. The result is a process physicists have named with grim accuracy spaghettification. The body is not just pulled, it is stretched vertically and crushed horizontally. The differential tidal forces would stretch the body along one axis and compress it along another, exceeding biological structural limits long before the horizon. In this scenario, the traveler never sees the inside. They are reduced to a stream of subatomic particles long before they cross the threshold. The secret of the interior remains safe because the observer is destroyed outside the door. But consider the giants. At the center of galaxies lie supermassive black holes, monsters with the mass of millions or billions of suns. Their event horizons are vast, stretching out for millions of kilometers. Because the hole is so large, the distance from the center to the horizon is immense. Consequently, the gravitational gradient at the boundary is surprisingly gentle. Here lies the density paradox. A black hole's radius is directly proportional to its mass, but its volume increases with the cube of the radius. This means that as a black hole grows in mass, its average density plummets. A stellar black hole is denser than an atomic nucleus, but a supermassive giant like M87 star has an average density lower than that of air. For the infalling astronaut approaching a supermassive black hole, there is no pain. The tidal forces at the horizon are negligible. They would feel weightless drifting through the dark. They could glance at their watch, check their vitals, and see nothing unusual. They would cross the event horizon, the point of no return, without a single warning or physical sensation. No barrier, no signpost, no jolt. Just a silent crossing into a region where space-time flows inward, faster than light. This is the true trap. The silence is the danger. The traveler passes from the realm of the living to the realm of the lost without even realizing the transition has occurred. They are alive, intact, and conscious. They can still see the universe they left behind. But they have unknowingly crossed a line of causality from which no signal can ever return. For a supermassive black hole, the crossing is silent, but surviving the boundary is misleading. Because crossing it changes everything the traveler thinks they know about light. You are now falling. The silence of the supermassive black hole has deceived you into thinking nothing has changed, but if you open your eyes, you will witness a sight no human has ever seen. It is a visual distortion so profound that it rewrites the geometry of the sky. As gravity accelerates you closer to the speed of light, the universe begins to warp. In normal life, your field of view is static, but at relativistic speeds, a phenomenon known as relativistic aberration or the searchlight effect takes hold. The light from the stars behind you, the safe universe you just left, does not stay behind you. As you speed up, the photons from the rear have to catch up to your eyes. This causes the entire panoramic view of the universe behind your ship to compress. Look out the window. The vast dome of stars that once filled the sky behind you is shrinking. It is being squeezed into a tighter and tighter circle, as if the universe is closing a door. Simultaneously, the blackness of the hole below isn't just approaching, it is rising up to meet you, swallowing your peripheral vision. It feels as though you are falling down an infinite dark tunnel, with the entire history of the cosmos compressed into a blindingly bright disk of light directly above your head. And the colors are wrong. The light falling in with you is gaining energy as it drops down the gravitational well, a process called gravitational blue shift. The soft yellow and white stars of the outer galaxy are shifting spectrum. They turn an angry electric blue, then a violent violet. If you could see into the invisible spectrum, the sky above would be blazing with hard X-rays and gamma radiation roasting the hull of your ship. Just before crossing the horizon, the traveler passes through the photon sphere, a region where gravity forces light into unstable circular orbits. For an instant, looking sideways would not reveal distant stars, but the back of their own helmet. They would be seeing photons that left their body looped around the black hole and returned to their eyes. It is a gravitational mirror ring, a warped echo of their own image suspended in curved space-time. Then the final shift happens. The bright disk of the universe above shrinks to a singularity of light, and the darkness closes in completely. You have crossed the line. You are inside. But while the traveler experiences a seamless fall, the universe outside witnesses a different story entirely. To the infalling traveler, the transition feels seamless. Life signs remain normal. The watch continues to tick. But as they fall deeper into the dark, something extraordinary happens to the image they left behind. The traveler moves forward into the curved abyss of space-time, yet to the outside universe, their final frame has frozen at the horizon, preserved as a fading imprint of light. Let us now shift our perspective. Imagine a colleague, a distant observer, watching this journey from the safety of a spaceship far beyond the gravitational pull. They are tracking the traveler's descent with a powerful telescope, waiting for the moment the ship breaches the darkness. But what they see breaks the logic of human intuition. According to the laws of general relativity, gravity does not just curve space, it drags time. As the traveler approaches the event horizon, the light bouncing off their ship has to climb out of an increasingly steep gravitational well to reach the observer. This climb drains the light of energy. The signals arrive with longer and longer gaps between them. To the distant observer, the traveler's movements begin to slow down. It starts as a cinematic, slow-motion effect. A wave of the hand that should take a second now takes an hour, then a day. As the traveler inches millimeters from the boundary, the image seems to grind to a halt. The light waves stretch out, shifting from the visible spectrum into deep red, then infrared, and finally into long, silent radio waves. This creates a profound paradox. To the observer, the traveler never crosses the horizon. The image of the ship is simply pasted onto the surface of the black hole, frozen in time, fading slowly into invisibility, but never truly disappearing. In the observer's reality, the traveler is trapped at the door for all eternity, a frozen image encoded at the boundary of space-time. But we know the truth. The traveler fell in hours ago. They are already gone. The image the observer sees is an optical echo, a glitch caused by the extreme delay of light fighting against gravity. This disagreement between the two perspectives is not an illusion. It is a fundamental feature of relativity. The universe has split into two valid yet contradictory timelines, one where the traveler stops forever and one where they continue into the dark. Relativity allows both timelines to coexist, one defined by light, the other by proper time. But the real impossibility begins after the crossing. Inside the horizon, the rules of the game change completely. If the outside world was governed by the familiar laws of motion, the interior is governed by a broken logic. This is where the black hole acts as a code breaker, rewriting the variables of our reality. In our normal universe, we have freedom of movement in space. You can go left or right, up or down. You can stop walking. You can turn around. The only thing you cannot control is time. Time marches forward relentlessly, dragging you from the past into the future. You cannot stop it, and you certainly cannot reverse it. Inside the event horizon, the Schwarzschild metric forecasts something extraordinary, a role reversal. The coordinate r, normally tied to distance, and the coordinate t, tied to time itself, swap identities. This means that inside a black hole, space becomes time. The direction towards the center is no longer a direction in space. It becomes a direction in time. Trying to fire your rockets to move away from the singularity is now as physically impossible as trying to prevent tomorrow from happening. You can move laterally, you can spin, you can fire engines until the fuel runs dry, but you will move towards the center with the same inevitability that seconds tick forward on a clock. This reveals the true nature of the singularity. It is not a thing sitting in the middle of a dark room. It is not a solid core that you will crash into. The singularity is a moment in your future. It is next Tuesday. It is an event that hasn't happened yet, but is as certain as the sunset. This geometry explains why there is no escape. To leave the black hole, you would not just need to move faster than light. You would need to travel backwards in time. The trap is not a wall that holds you in. It is a timeline that has collapsed into a single destination. As the traveler drifts toward this final moment, the tidal forces of the singularity begin to dominate, creating a curvature so infinite that physics itself gives up. But if every path leads to the center and no signal can escape, does the traveler's existence simply vanish? Does the universe delete the file? Physics says no. It says the data must change format. We have established that the traveler is trapped in a future singularity, their physical form crushed into a point of infinite density. But what happens to the information that made them who they were? This question leads us to the deepest conflict in modern physics, the information paradox. In our universe, quantum mechanics relies on a sacred rule: information is never destroyed. If you burn a book, the information is not technically lost. It is scrambled into ash and smoke. If you could capture every particle of smoke and every photon of heat, you could, in theory, reconstruct the text. But a black hole seems to violate this rule. If the book falls in and the black hole eventually disappears, where did the story go? The solution proposed by physicists Gerard 't Hooft and Leonard Susskind fundamentally changes our perception of reality. They suggest that when a 3D object falls into a black hole, its information is not lost inside the volume of the hole. Instead, it is smeared across the surface of the event horizon. This is the holographic principle. Everything inside a three-dimensional space can, in theory, be rewritten on a two-dimensional surface. And as an object crosses the horizon, its quantum blueprint, the record of what it is, becomes etched onto the surface of the black hole as a shimmering layer of information. In this view, the black hole is not a dungeon. It is a hard drive. It is the ultimate cosmic archive, storing the data of everything it has ever consumed. You are not gone. You have simply been converted from matter into bits stored on the edge of the abyss. This suggests a terrifying possibility that our entire 3D universe might just be a hologram projected from a distant 2D boundary. We might be living inside the projection of a black hole right now. But even hard drives do not last forever. You are stored on the edge, preserved in the cold code of the horizon. But nothing lasts forever, not even black holes. To see the final fate of our traveler and of the black hole itself, we must leave the present era and accelerate the clock. We must zoom out to the deep time of the cosmos, a scale where the entire history of humanity is less than a single tick of the second hand. In the short term, meaning the next few trillion years, black holes will be the rulers of the dark. As the universe expands and galaxies drift apart, star formation will cease. The last red dwarfs will fade into white dwarfs, then cool into black dwarfs. If theories of proton decay are correct, even normal matter will eventually dissolve, leaving the universe as an empty void populated only by black holes. This is the black hole era. In this desolate future, these objects will be the only sources of complexity, left silent sentinels drifting through a universe that is stretched into near infinite cold. But they are not immortal. In 1974, Stephen Hawking discovered that black holes leak. Through a quantum process now known as Hawking radiation, black holes emit particles. They slowly lose mass over time. Currently, the universe is too hot for this to matter. Black holes absorb more energy from the cosmic background than they emit. But in the far future, as the universe cools toward absolute zero, the evaporation will begin in earnest. This process is agonizingly slow. A black hole with the mass of the sun will take 10 to the power of 67 years to evaporate. For a supermassive monster like the one at the center of M87 star, the timescale stretches to 10 to the power of 100 years, a Google years. It is a duration so vast that it makes the concept of eternity seem short, yet the clock is ticking. As it evaporates, the black hole releases not only energy, but entropy, slowly returning its stored quantum information to the universe. As it gets smaller, it gets hotter and emits radiation faster. In its final moments after eons of silence, the black hole does not fade away gently. It explodes. The last remnants of its mass are converted into a brilliant flash of high-energy gamma rays. And here lies the final twist of the pinhole paradox we started with. The black hole does not drain the pool of the universe. The universe expands and cools until the pool itself evaporates, leaving the black holes to dry up one by one. When the last black hole evaporates, releasing its stored energy back into the void, the story of the universe is finally complete. The cosmic archive deletes itself. Or perhaps, as some theories suggest, that final burst of radiation releases the information back into the universe, a final breath that carries the scrambled data of everything that ever fell in returning it to the cosmos, in a final act of redemption. So we return to our initial fear as the black hole, a flaw in the cosmos, a drain that will empty the universe of its substance. The answer revealed by the physics of the eternal is a resounding no. Far from being cosmic villains, black holes are the most efficient engines nature has ever created. They are the architects of galaxies, anchoring the swirls of stars that gave birth to us. They are the crucibles where the laws of physics are tested to their absolute limit. And ultimately, they are the preservers. In a universe destined for cold and silence, where every star will eventually burn out and every civilization will fade, black holes remain. They are the last bastions of energy in a dying cosmos, holding on to the heat of creation long after the lights have gone out. The journey we have taken from the violent rapids of the accretion disk across the silent boundary of the event horizon and down into the geometric madness of the singularity teaches us one profound truth. General relativity shows a universe where geometry behaves like matter and where time and space exchange roles under extreme curvature. And death in the eyes of quantum mechanics is not deletion, it is transformation. The traveler who fell in did not simply vanish from the book of the universe, they were rewritten. Their story was encoded onto the horizon, preserved in the holographic memory of gravity, and eventually returned to the cosmos in a final breath of light billions of years later. We may never personally survive the journey into the abyss. The physical body is fragile, bound by the limits of biology, but the laws that govern us suggest a strange kind of immortality. The traveler may fall, but the universe does not forget. And the paradox that began with a fall ends with a memory that outlives the cosmos itself.